All right, today we're going to dive into the Rabin-Karp algorithm. It's a really fascinating way to find text inside of a bigger document. And its secret sauce is this incredibly powerful but surprisingly simple idea called the rolling hash.
You ever hit Control F on a huge web page and wonder how it just instantly finds what you're looking for? It feels like magic, right? But behind that is a classic computer science problem. How do you efficiently search for a small string, what we call a pattern, inside a much larger text?
The biggest hurdle here, really, is speed. When the texts get massive, we're talking entire books, articles, or even sequences of DNA, the most obvious, straightforward way of searching just completely falls apart. It just doesn't scale. So what's that simple but slow way? Well, you take your pattern, you line it up at the very beginning of the text, and you check it, character by character. No match? Okay, slide the pattern over by just one position and do it all again, and again, and again. This is what we call O of n times m complexity. All that really means is for a long text and a long pattern, the number of checks you have to do just explodes. You'd be waiting forever.
This is where Rabin-Karp gets really clever. Instead of comparing strings of letters, what if, we could turn each string into a single unique number, kind of like a digital fingerprint. Then we could just compare the numbers, and that would be way faster. This whole idea is called hashing.
You know, this barcode analogy is perfect. Think about it. You figure out the barcode for the item you want once. Then you can just zip down the aisle, quickly scanning the barcode of every little section on the shelf. You only stop to take a closer look when you hear that beep, when you find a matching barcode. That is the exact strategy behind Rabin-Karp.
Okay, so let's make this real. Imagine we're trying to find this specific four-letter pattern, kata, inside a huge document.
So using the algorithm's hashing function, we can take this word, these letters,
and turn it into this one single number. Now, instead of juggling 4 different characters, we just have to look for this one integer. This is the fingerprint, the hash value for kata. But wait a second. If we have to calculate a brand new hash for every single 4-letter chunk of text, are we really saving any time? Honestly, not really. And this is where the algorithm pulls out its secret weapon, the rolling hash.
See, here's the crucial insight. We don't recalculate the hash from scratch every time we slide our little window one spot to the right. No, instead, we do a super quick and clever update.
And here's how that update works. It's a simple 3-step dance. First, as the window slides, you mathematically subtract the value of the character that just fell off the end. Second, you shift everything that's left over. And third, you add in the value of the new character that just slid into the window. Because this little operation takes the same amount of time no matter how long the pattern is, we call it a constant time, or O of 1 update. This is the engine that makes the whole thing run so fast.
Now, this all sounds a little too perfect, doesn't it? There is one catch, and it's a big one we absolutely have to deal with. What happens if 2 totally different strings just happen to create the exact same fingerprint?
That's called a hash collision. Now, if you have a good hash function, it's pretty rare, but it can happen. For instance, maybe the string ABFC, just by pure chance, ends up with the same hash value as kata. So the rule is simple and non-negotiable. If the hashes match, you must then do a final character-by-character check to prove it's a real match and not just a fluke. So this brings us to performance. On a normal day, when collisions aren't happening much, Rabin-Karp is lightning fast. It runs in what we call linear time, O of n plus m, which just means its speed is tied directly to the size of the text. But, and it's a big but, in a worst-case scenario, if you have a terrible hash function that's causing collisions all over the place, it can slow right back down to that original, painful, brute force speed. So with that trade-off in mind, when should you actually pull this tool out of your toolbox instead of one of the other famous string searching algorithms? Let's see how it stacks up. If you look at this table, you'll see algorithms like KMP which actually guarantee fast performance no matter what. And Boyer Moore is often even faster in practice. So at first glance, Rabin-Karp might seem less useful. But it has a very specific superpower. Its superpower really shines when you're not just looking for one pattern, but for a whole bunch of them, and they're all the same length. You can just calculate the hash for every single one of your patterns, throw them into a set, and then as you're rolling your hash through the text, you check against that entire set at once. That's something the other guys can't do nearly as well. Okay, let's boil all this down. What are the absolute key things you need to remember from all this? First, the magic is in that constant time ov1 rolling hash update. That's the engine. Second, in the real world, its performance is fantastic, linear time. Third, and you can never forget this, always verify a hash match to deal with those pesky collisions. And finally, remember its niche, its special power. It's the champ at searching for lots of patterns that are all the same length.
So I'll leave you with a final thought to chew on. How could you take this powerful fingerprinting idea and level it up? Instead of just finding one word, could you use rolling hashes to efficiently find all the matching sentences or even paragraphs between two massive books to check for plagiarism? It's a really cool problem that shows you just how flexible this whole concept really is.